Welcome to the product training module for the NTCLE317 temperature sensor, a small bead diameter NTC component with peak insulated silver-plated nickel iron special alloy wires. The design of this part will ensure fast, accurate, and reliable temperature sensing in applications across all market segments. The NTCLE317 has two insulated nickel iron alloy wires, which have the lowest thermal conductivity for a temperature sensor on the market. Thus, there is minimal heat loss along the wire length at steady state, and there is also no temperature gradient. Consequently, it provides an ultimate temperature measurement accuracy on hot spots. The bead dimension is restricted to 1.6 millimeters max, compared to 2.4 millimeters for its NTCLE300 predecessor, and the response time in stirred air is now around 3 seconds compared to 6 seconds for NTCLE300. Tight electrical tolerances are ensured by small resistance distribution spreads and stringent electrical sorting in production. This enables production to achieve a temperature accuracy of plus or minus 0.5 degrees centigrade on a range. Finally, the bead coating epoxy has a good adhesion to the peak insulation of the wire, which ensures a robust resistance to harsh conditions, even for those small bead dimensions. The NTCLE317 temperature sensor can be used widely for automotive and industrial applications. Specific examples include body control applications, such as seat heating in cars, thanks to the wire flexibility and excellent moisture resistance, and boiler water heater clip sensors due to the temperature accuracy. It can also be involved in electric traction temperature sensors in HEV/EV vehicles. The NTCLE317 can be integrated in battery packs or in fire and smoke detectors as well, where it will detect fast temperature risings in an effective way. NTCLE317 is the dream-made-true component for fast and reliable design-in efforts. The AEC-Q200 reliability test results show that NTCLE317 can be used for nearly all temperature sensing in automotive and like applications. 3D models can be provided on request, and resistance versus temperature curve tables can be downloaded via the online calculator. Finally, a dynamic SPICE model where the temperature is represented by a virtual voltage is available for circuit simulation. The model provides the engineer with a unique yet precise look into the component functionality and performance expectations when incorporated in the customer's specific application. Let's open now LT SPICE 17 and let's demonstrate the accuracy of the NTCLE317 thermistor. This component develops here a temperature-dependent voltage which is filtered, sampled and holed, quantized, and finally converted into a temperature readout by a microprocessor. During a transient simulation of a temperature change from -55 centigrade up to 150 centigrade, we measure the difference between the readout and the real temperature of the thermistor. The simulation speed is very high. We perform a Monte Carlo analysis where the NTCLE317 tolerances are swept randomly. When the simulation is over, we have a complete picture of the measurement accuracy in function of the temperature, and we see that the SPICE model reproduces exactly the product specification. In conclusion, the thermal response curve of the NTCLE317 in comparison with preceding product ranges is highlighted. It is noted that the blue curve of the NTCLE317 reacts much faster than other ranges with bigger bead dimensions, namely NTCLE100 and NTCLE300. When comparing the NTCLE317 to NTCLE305, which has the same small dimensions but with the original nickel wires, the NTCLE317 with its special alloy wires presents nearly no gradient of temperature at steady state. NTCLE317 can in turn be declared as the most accurate and fastest temperature sensing component within the Vishay NTCLE ranges.